नमस्कार, सुस्वागतम, केम छो, आदाबार्स, गुड आफ्टरनून। आप सभी का पीआरएल के अमृत व्याख्यान में स्वागत है, अभिनंदन है। A very warm welcome from me, Anil Bharadwaj, for the PRL का अमृत व्याख्यान. Today is the 56th व्याख्यान of the 75 episodes series of व्याख्यान, which is being organized as a part of PRL's 75 years of legacy and history in fundamental physics and space sciences. Established in the year 1947 by the father of Indian space program, Dr. Vikram Sarabhai, the PRL's Platinum Jubilee coincides with India's 75 years of independence. Hence, it's a joint celebration of the development of science and technology in India by PRL under the banner of PRL Kamrit Vyakhyaan. Today, we have yet another very distinguished Vyakhyaan Dr. Sumit Chopra, who is the Director of Institute of Seismological Research in Gandhinagar. And he's going to talk to us on seismological research and Gujarat's initiative. We thank Dr. Sumit Chopra for accepting our invitation and to be with us today at the PRL Kamrit Vyakhyaan, which is being organized as a part of Platinum Jubilee of PRL and Azadi Kamrit Mahotsav. I now request my colleague, Professor Pallam Raju, kindly introduce our today's Vyakhyaan Karta to the panel on the WebEx, as well as those who have joined us live on the PRL YouTube channel. Over to you, Dr. Pallam Raju.
Good afternoon. Thank you, Professor Bharadwaj. It's indeed a pleasure for me to invite and introduce our speaker for the day, Dr. Sumit Chopra. He did his MTech from IIT Roorkee and PhD from Kurukshetra University in Applied Geophysics. He worked with the Sardar Sarovar Narmada Nigam Limited, a wholly owned company of government of Gujarat, for 15 years, wherein he monitored the seismic activity in the environs of Narmada Dam. After 2001 unfortunate Bhuj earthquake, government of Gujarat has established Institute of Seismological Research at Gandhinagar. And Dr. Chopra was deputed to ISR, wherein he established a dense network of broadband seismographs, strong motion accelerographs, and permanent GPS stations all over the state of Gujarat. He has carried out site-specific response studies for critical structures like LNG terminals, nuclear power plants, special investment regions, etc. Dr. Chopra joined the Seismology Division of the Ministry of Earth Sciences in 2010. He headed the Earthquake Hazard and Risk Analysis Division of the newly established National Center for Seismology of the Ministry of Earth Sciences during 2011 to 15. In 2015, he was appointed as a director of Institute of Seismological Research. That's where he continues till date. Dr. Chopra's thrust areas of research are deterministic and probabilistic seismic hazard analysis, estimation of source parameters, site-specific response studies, shallow crustal studies using RF approach, site characterization, and attenuation characterization. He has more than 30 years of experience in seismological research. He has more than 100 scientific research peer-reviewed publications and more than 100 scientific technical publications to his credit. He has guided several PhD students. He has been awarded Certificate of Merit in 2015 by Ministry of Earth Sciences for his outstanding contribution in geosciences. He is a member of the Research Advisory Committee of National Center for Seismology, Ministry of Earth Sciences, Government of India, member of studies for nuclear power plant sites, and member of Technical Committee for Characterization of Seismological Zones around the sites and evaluation and response of soil strata to vibratory ground motion, and member of several other committees. He is all, including Board of Studies of Changai University of Science and Technology in Anand. I would also like to recollect at this time that he and ISR had supported the seismic study of rock and soil at PRL's Guru Shikhar Observatory at 2.45 meter telescope at Guru Shikhar, and he provided a lot of support for that. With this few words, I will now invite Dr. Sumer Chopra to deliver the 56th PRL Amrut Vyakhyaan on seismological research and Gujarat's initiatives. Over to you, Dr. Chopra.
Thank you. Namaskar, Dr. Pallam Raju, and namaskar to all the dignitaries who have joined, and special thanks to the director PRL, Shri Bhardwaj ji, for inviting me for this Vyakhyaan. So I'm happy to be a part of this, you can say, a series of lectures, which are very important for the young generation. And I'll give you a brief today talk, not very, you can say, hardcore seismology, just a brief introduction about different aspects. I'll just share my presentation here. So I'll give you a talk on seismological research and the initiative what Gujarat government has taken after the devastating 2001 Bhuj earthquakes. So I'll give you a brief introduction about how the earthquakes generally occur inside the earth, how they are formed, what are the factors responsible for the initiation of earthquakes. A brief introduction, not hardcore, very, you can say, very a general public can also understand this. And the first question comes in our mind is, what is seismology? And most of the people generally knows that seismology is a science dealing with all the aspects related to earthquakes. Means occurrence of earthquakes, how the earthquakes are occurring, distribution of earthquakes. And there are different branches, you can say sub branches of this seismology also. The main branches are observational seismology, then engineering seismology, physical seismology, and exploration seismology. Generally, the observation seismology deals with the recording of earthquakes. What we do generally, we install a number of seismograph stations all over the region, and then we record the earthquakes. Then we prepare the catalog of earthquakes of different magnitude, and we also observe the earthquake effects. In engineering seismology, which is very useful for the engineers, we generally estimate the seismic hazard and risk and provide the site-specific response spectra to all the engineering community for designing of a seismic design of different infrastructure. And then there is one branch called physical seismology. In physical seismology, generally we study the properties of the earth and the physical characteristics of seismic sources. And the more important thing is that exploration seismology. You can see the best example is the oil industry. Oil industry is using the benefits and advantages of this exploration seismology, or the research which has been done in last 50 to 100 years in the field of seismology. So they are utilizing that benefit. And if we see seismology is a multidisciplinary science. It generally links physics with other geoscientific disciplines like geography, geology, geochemistry. And this is an international science, means it does not have any physical boundaries, or you can say geographical boundaries. And we generally deal with large span of amplitudes ranging from nanometers to tens of meters. We also deal with very large span of wave periods from microseconds to tens of thousands of seconds. And this is a very young science. It evolved in only in 19th century. And there are so many myths and legends which are associated with earthquakes. In Hindu mythology, what people believe that Earth is carried on their head by 8 elephants.
Hello.
Dr. Chopra, you're muted for some reason.
Looks like some connectivity problem at his end.
Look into inside the Earth. What are the different major layers inside the Earth? As most of the people, I think, in dealing with the working in geoscience community, they all know that Earth is composed of mostly 3 divisions: the crust and mantle and core. And the crust is around, you can say, 20 to 50 kilometers thick, Then after crust, there is a mantle. Mantle is almost around 2900 to 3000 kilometer thick. And then there is an inner core. You can say a core which has an outer core and inner core. Outer core is in the form of liquid and inner core is the solid. And the thickness is around 3200 to, you can say, 3300 kilometers. And the total, you can say, radius of the earth is around 6371 kilometers. And there are also some different aspects. There are also different layers: lithosphere, asthenosphere, and mesosphere. These are also defined. The top, you can say, 100 kilometer thick layer, which is cool, rigid, and brittle, is called generally a lithospheric layer. Then there is below the lithosphere is an asthenosphere, which is hot, which composed of hot material, weak and plastic, and the thickness is around, you can say, 200 kilometers, around 200 kilometers. And below that, mesosphere is there, which is very hot, but it is stronger than the asthenosphere because due to the high pressure. And there are different, since there are three, you can say, crust is there, then mantle is there, and then the core is also there. So there are different discontinuities between these three layers. So a brief history is like who discovered that layer. The crust mantle boundary is generally called, we call it a Moho boundary, or Mohoro, which was a scientist. He discovered this boundary in 1909. Then core was discovered by Oldham in 1906, and the boundary, the core mantle boundary, is called the Gutenberg boundary. So the name was given in 1914, and it is around 2900 below the surface. And the Jeffreys proposed the theory that the outer core is in the liquid in 1926, and inner core was discovered by 1936 by Lehman. And it is very interesting to see that all these boundaries were discovered because nobody can drill up to the center of the earth. The maximum hole that has been drilled in the historical past is only up to 10 to 11 kilometers deep we can go, because the technology is not available to drill to go beyond 10 to 11 kilometers. So all these boundaries were discovered from the, you can say, the knowledge of by recording the earthquake waves, because the earthquake waves generally when they travel inside the earth, they strike different boundaries. They strike the crust mantle boundary, then they strike the mantle and core boundary, and the different kind of waves are, you can say, reflected by these boundaries. And by studying those waveforms, these boundaries has been discovered by different scientists. And now the basic question occurs: why the earthquake occurs, and why the earthquakes epicenters are not uniformly distributed around the globe, and generally at what depth these earthquakes generally occur. And there is one theory which was proposed, become popular in 1960s, that is called a plate tectonics. And this theory generally provides most of the fundamental questions, all the above three questions about the seismology. And if you see the distribution of earthquakes in last 100 years around the globe, you can see that earthquakes are not everywhere. They are not epicenters. The epicenters are not distributed uniformly. They are around in some, you can say, some zones. So only these are located in some zones. And if we see the major tectonic plates of the world, which composes of 8 major tectonic plates: African plate, Eurasian plate, then North American plate, South American plate, Pacific plate, Australian plate, and Antarctic plate. And if we compare these two figures, you can see this: most of the earthquakes are generally at the boundary of between these two different plates. So these plates boundaries generally generate most of the earthquakes. And these plates are not stationary. These plates are relatively moving against each other, across each other. They converge, they diverge, and they move past each other also with different velocities. And what is the relation between seismicity and plate tectonics? The majority of earthquakes we can see that occur at the location or close to the plate boundaries. These are called plate boundaries earthquakes. And along these plate boundaries earthquakes, almost 75% of the earthquakes are in the circum-Pacific belt, and 22% are located in the alpine Himalayan belt, and 2% in the ocean spreading ridges. Therefore, we can see that the knowledge and direction, and to study, if we study the direction and velocity of these plate motions, we can easily understand the earthquake processes. And as I already told you, that plate tectonics mostly explains most of the questions related to the earthquake occurrence, distribution of earthquakes around the globe, geographical differences in different type of earthquakes, then spatial distribution of largest earthquakes, and relative frequency of the earthquakes also. And if you see the frequency of earthquakes, how many earthquakes of what magnitude occur, you can say annually. And you can say great earthquakes, the earthquake which has a magnitude of more than 8 are called great earthquakes, and generally the frequency is around 1 to 2 per year anywhere in the world. Then the magnitude range between 7 to 7.9 are called major earthquakes. Around 18 to 20 earthquakes, they occur around the world every year. Then strong earthquakes 120, which having a magnitude of between 6 to 6.9. And if we go down to minor earthquakes of less than, you can say, 2 magnitude, almost thousands of earthquakes occur everywhere on the globe. And if we see the distribution of global earthquake in last 120 years, since 1900, as I already told you, the global great earthquake means magnitude more than 8. And you can see these are mostly uniformly distributed, almost 1 to 2 earthquakes per year. But if we see closely, after 2004, this Sumatra earthquake of magnitude almost 9.1, we have recorded almost, I think, 5 to 6 earthquakes, great earthquakes of magnitude more than 8 in the world. And now the basic questions arise: how earthquakes occur? Generally, the earthquake occurs along faults. And what are faults? Faults are weak zones separating two geological blocks. And generally, tectonic forces which drives these different plates, they cause the blocks to move relative to each other. And to explain this earthquake occurrence, there is a very theory called elastic rebound theory that was proposed by John Reed in 1906 after this, you can say, San Andreas earthquake. So what this theory says, you can see there is in the left side, I'll just have a pointer. Yeah, you can see this is a kind of ground where a road is there which is straight, and due to the movement of the plates and different these already the area is under, you can say, lot of stress is being applied to this area. This is under a lot of strain energy, and the strain energy generally accumulates, and this area is not deformed due to the, you can apply when we apply the stress. And when the fault ruptures when the strength, the applied stress, you can say, overshoots the strength of the rocks, then the rupture occurs, and the generally earthquake occurs at that time. And this is explained here also. You can see this is an area where a fence is there, and then we apply the stress, the rocks are deformed. This you can see fence is also getting deformed, and there is when the stress within the rocks exceeds the friction, then the rupture occurs, and there is a definite movement, and then earthquakes occurs. And then the different seismic waves generally travels from this, you can say, fault, and these are being recorded at different stations which are deployed all over the region. And it is very interesting to note that most of the strain energy during an earthquake occurrence, this is converted into heat. Only a few percent, you can say 4 to 5% is converted into seismic waves. But these are still enough, and these are very, you can say, powerful to generate, you can say, to topple or to for powerful shaking and these topples generally big structures also. If the magnitude we have seen that during a great earthquakes like the Sumatra earthquake, how devastating it was. Most of the, you can say, around the epicenter, if the magnitude is more than 8, then most of the structures get damaged due to these earthquakes. And these are very typical seismograms, you can say, recorded in of magnitude 6.5. The station is in Germany, and the earthquake was in Japan. And there are different kinds. Whenever the earthquakes, you can say, travels, you can emanates from a focus of that earthquake, you can say, place. Then different kind of waves are generated, which are called body waves and surface waves. And then body wave generally travels in the body of the medium, and surface wave generally travels along the surface of the, you can say, medium. And there are different kind of body waves, P waves and S waves. In the P waves, this is called primary waves. The particle motion is generally along the direction of propagation, and S waves are called shear wave or secondary waves, where the particle motion is perpendicular to the direction of propagation. Then there are different kind of surface waves also called Rayleigh waves and Love waves. And generally we record this in 3 components. We can say vertical component, north, south, and east, west component. And these are being, this is a record of a instrument called seismograph. Generally seismograph is a very, physically it is a very simple instrument. It just comprises of a spring and you can say mass and a spring. So one of the thing is fixed. So whenever there is a differential movement due to the you can say earthquake waves. Then there is a movement between the mass and the spring, and these are being recorded on a chart paper. Here, what we are doing, the mechanical energy is converted into the, you can say, electrical energy, and we record this in terms of counts or millivolts. And generally, in ancient, in historical times, there were different kind of instrument to record different, you can say, earthquakes. I mean, there are, if we are recording any earthquake in Ahmedabad or Gandhinagar, if the earthquake epicenter is very near to the, you can say, your recording point, these are called local earthquakes. Then if the epicenter is more than 300, 400 kilometers, then this is called a regional earthquakes. And if the epicenter is more than 700 or 1000 kilometers, then we call it a long distance earthquake or teleseismic earthquakes. So earlier, what we used to do, we have a different kind of instrument to record different earthquakes. Means we have a short period seismograph to record local earthquakes. Then we have a long period seismograph to record its regional and teleseismic earthquakes. Now the technology in last 30 years has been developed. They have housed all these instruments in a, you can say, single housing type instrument that is called a broadband seismograph. And the broadband seismogram, what it does, it records all the kind of earthquakes. It records local earthquakes also, it records regional earthquakes also, and it records global earthquakes also. And this I already told you. Let us speak. And let us see the different, the Bureau of Indian Standard has published a seismic zoning map, which is being revised from time to time. And the latest seismic map is showed in this slide, and it comprises of 4 seismic zones. So India is divided into 4 seismic zones from zone 2 to zone 5. So zone 5, the areas which are falling under zone 5 has the maximum seismic hazard, and the areas falling under zone 2 depicted in the blue color, mostly in the peninsular part of India. So these are having the lowest seismic hazard. And if we convert this into hazard into magnitude, means zone 5 can expect a magnitude of earthquake up to 8 magnitude, zone 4 can expect earthquakes of magnitude up to 7, zone 3 up to 6, and zone 2 up to 5 magnitude earthquake. And if we add the area, you can see almost more than 50% of the Indian area are, you can say, liable for an earthquake of magnitude 6 or greater. And why these earthquakes are happening in India? Most because in Indian region, this is the Himalayan is an active plate boundary between, just I told you about the plate tectonics theory. So there is one Indian plates. So this is the plate boundary between an Indian plate, where the Indian plate is subducting beneath the Eurasian plate. So due to the collision of these two plates, the Himalayas has been formed. And there is one scientist, Roger Wilhelm. He is based on this, you can say, slip, or you can say the this collision of Indian plate with the, you can say, Eurasian plate, because whenever the collision takes place, the stresses are being transferred on the rocks. Those are at the, you can say, surface or at up to depth of 30 to 40 kilometers. And he has calculated the earthquake potential of different seismic zones from, you can say, from the Karakoram ranges to the northeast up to, you can say, up to Arunachal Pradesh. And some major great earthquakes have already happened in Himalayan region, like 1905 Kangra earthquakes, then 1934 Bihar Nepal earthquake. Then there is 2 earthquakes has happened here in 1950, Great Assam earthquakes, and 1897 the Shillong earthquakes. So most of the energy, you can say, strain energy has already been released due to these earthquakes. But there are certain areas, gap areas, where the still a lot of strain energy has already been accumulated, where a great earthquakes of magnitude 8 can happen. Just like you can see in Almora region. Here the last earthquake, the great earthquake, was in 1803. Now the strain energy has been accumulated in last more than 200 years. So a magnitude 8 earthquake can happen here anytime. And then in Kishtwar area, you can say 8.4. This is Nahan area in Himachal Pradesh, 8.4. And this is a central gap where you can say the combined, if an earthquake rupture all this almost around more than 200 kilometers, then earthquakes 8.7 magnitude earthquake can happen anywhere. Then eastern Bhutan also, and Arunachal also. So you can, by looking into this figure, you can say that Himalaya is due for a great earthquakes. And when this great earthquake will occur, nobody can tell us the time. It may happen tomorrow, it may happen day after tomorrow, maybe after 100 years, maybe after 50 years. But it is very difficult to, because we cannot predict and earthquakes. But still a lot of strain energy is already stored in this in the Himalayan belt. And these are the significant earthquakes which has happened in last, you can say, last 200 years. The major earthquakes that has started in 1819, that was a Kutch earthquake of magnitude of almost around 8. So now they have revised the earthquake, the magnitude, the movement magnitude was around 7.8. Then there was a Shillong plateau. These reds are depicting the great earthquakes of magnitude more than 8. So last great earthquake which has happened, you can say in Indian region, is 1950, this great Assam earthquake. So after that, there was no great earthquake in the Indian region. And this is the seismicity in last 500 years. You can see this map, Indian map. You can see most of the earthquakes are in this region. This is a Himalayan. This is a active plate boundary. And the earthquakes which are happening inside the plate boundary, means inside the Indian plate. This is an Indian plates. These are called intraplate earthquakes, because lot of the stress, whenever there is a collision between two plates, lot of the stress generally transferred to the, you can say, back stress also is being transferred to this peninsular part of the India also. So here also earthquakes may happen, but the, you can say, frequency of earthquakes and recurrence interval will be large. Here the recurrence interval of, you can say, a magnitude 6 earthquakes is around 500 to 1000 years, whereas in the Himalayan region the recurrence interval is around, you can say, 50 years or 30 to 50 years. So, and these are the major earthquakes, and you can say casualties almost in the last, you can say, 20 to 30 years, the almost 34,000 people generally lost their lives due to the earthquakes in this Indian region only. And if you see the distribution of earthquakes in region wise in the last 110 years, we see that the most of the earthquakes are in the northeast region, and the entire northeast region has been placed in zone 5 as per the seismic zoning map of India, where an earthquake of magnitude 8 plus can happen. And if you see in the last 110 years, almost 200 earthquakes of more than 5 to 5.9 has happened, 128 earthquakes of 6 to 6.9, 15 earthquakes of 7 to 7.9, and 4 earthquakes of magnitude more than 8 in the last 110 years. And if we compare with the central Himalaya, where 68 earthquakes of 5 to 5.9, 28, 4 and 1. And if you see this entire Himalayan belt, so this belt, and this is a subduction zone, Andaman Nicobar Island. So this, most of the earthquakes are happening here only. Though very few earthquakes are happened in Kutch region and peninsular India, but only one earthquake of magnitude 8, that was in 1819. That is being debated whether that is a great earthquake or near to the great earthquakes. Only that earthquake has magnitude near to 8. Otherwise, most of the earthquakes are having magnitude between 6 to 6.5 in this Indo-Gangetic plain, in this peninsular part of India. And the earthquake hazard in India is due to the, you can say, earthquakes from the Himalayan region. Then earthquakes may happen beneath the ocean, and earthquakes are happening in plate interior also, which are considered to be a stable continental region. And then there is an earthquake from reservoir induced earthquakes are also happening in Indian. The classic example is the Koyna region, where an earthquake of magnitude, you can say, 6.3 happened in 1967. So after they have constructed a dam there near Koyna. So after the filling of the reservoir, previously there were hardly any seismicity noticed in that region, but they have noticed that after the filling of the reservoir, the seismicity has increased drastically, and thousands of earthquakes or small earthquakes occurred in that region and still occurring in this region. And one of the earthquakes, major, the maximum magnitude they have recorded is around 6.3. That was called a Koyna earthquake. And recently also one more category that has come in this, you can say, earthquake hazard for Indian region is a monsoon-induced seismicity. So we have noticed that there are few pockets in Indian region where after intense monsoon, generally very swarm type of earthquake activity happens in that region. And the classic example, 2 or 3 regions are there in Saurashtra region of Gujarat. One is in the Jamnagar region, and another one region which is in the, you can say, in the Talala region, Gir forest region, where the lion sanctuary is there. So where there we have noticed in the last 10 to 15 years of recording earthquakes that after intense monsoon, generally a swarm type of activity is noticed in that region. That generally occurs in the month of September. Then it continued up to the month of, you can say, January, and after January it subsides. So every year, almost every year, we are recording earthquakes from that region. So we generally gave it a term, it's called monsoon induced seismicity. And what are the, you can say, how the earthquake generally affects our lifeline structures or our different structures. Generally, earthquake damage can be in terms of ground failure, due to which the construction or infrastructure collapses. Then fires can also happen due to earthquakes. These are also, fire is a secondary effect. And because of the broken gas and electrical lines, then earthquake can also trigger landslides. Then it can also trigger a phenomena called liquefaction. So what is liquefaction? So whenever there is the water table is very shallow, and you can say the alluvium type or sandy type of, soil is there. So when these earthquake waves, intense earthquake waves or the large ground motion generally travel to that region, generally the soil loses its strength and it behaves like a liquid. So that phenomenon is called a liquefaction. Then another earthquake effect is a tsunami. If there is a large earthquake that happens in you can say sea, and there is a definite vertical movement during that earthquake, a large you can say volume of water get displaced, and due to this, tsunamis are generated. And in historical past, it can record an tsunami up to 65 meters have also been recorded. Then the question arises, how to mitigate the earthquake damages? Because we cannot stop the earthquakes. We have to live with this earthquake activity.
Dr. Chopra, yeah,
Yes.
just to make sure whether your slide is moving, I do not know that.
Yeah, I'm in the earthquake damage slide. Now it is moving.
At least in my side, I cannot see moving. I do not know about others.
Yeah, it is moving.
Moving, okay, good. Because I also received call from Busit, so just okay. Please go ahead.
Okay.
So,
So we can mitigate the earthquake effects for doing the assessing the seismic hazard and doing the microzonation. Then the question arises, why the microzonation is required and how it can be utilized. Generally, what the seismic zonation, they generally identify the regions and which have, you can say, different, because a local, due to the earthquake effect, the effect of earthquake will be different in different geological conditions. So generally we have to, you can say, assess the earthquake hazard zone wise also. So that is why zonation is required. And this information is utilized by generally engineers and planners when they, you can say, develop a site. You can say when they develop the infrastructure, so they utilize this kind of information, earthquake microzonation or hazard assessment, which has been done by any agency. And what are the controlling factors of seismic hazards? So these are the controlling factors: magnitude, focal depth, proximity to a fault, then fault type, soil conditions, and building characteristics. So these are the different factors that controls the seismic hazard.
looks like your slide is not moving. At least I am stuck at earthquake hazard for Indian region.
And if we see the tectonic map of India, just I told you the faults are the major factors that generate an earthquake. So you can say Indian landmass is, you can say, scattered with a number of faults. This earthquake, this Himalayan region has a number of major faults: main boundary fault, main source. Then in the central India we have a Narmada zone fault. Then there are different Godavari grabeners also. So India is, you can say, crisscrossed by a number of faults. And when we do the seismic hazard assessment, generally this requires, you can say, there are three major components of seismic hazard assessment. We have to estimate, or we have to assess the seismic, you can say, source effect. Then we have to path effect and site response effect. Because whenever the earthquakes starts from you can say faults, then the different waves are traveled. So we have to assess the seismic source characteristics, then path characteristics, and we have to assess the local site conditions also. And in this part, the local site response is a very important thing, because most of the modification in the seismic waves generally happens due to the local site effect. So it is very important to study the local site effects. And if we see the site classification map of India, you can say almost more than 51% of area, this yellow portion, this is being covered by stiff soil. Stiff soil means where the velocity, the shear wave velocity is less than, you can say, it is less than 700, it is less than 360, means between 180 to 360 meter per second. So these are the regions which are comprises of quaternary sediments. Quaternary sediments are this which are of age around 10,000, you can say, which are of Holocene area, Holocene period. So these sediments are very loose sediments. These are not consolidated, and whenever earthquakes generally happen or the wave travels in this medium, generally the waves get amplified. So it is very important to locate this kind of region and study the site response in this region. And as I already told you, the local site conditions generally they affect the amplitude, frequency, content, and duration. But they affect the amplitude. They may amplify also ground motion, and sometimes, if the conditions are suitable, they de-amplify the ground motions also. And but the you can say effect in the frequency content, they may shift. These you can say ground condition may shift the frequency content of the incoming seismic waves to the higher or the lower you can say frequency bands, and they may extend the duration of the ground shaking also. So it is very important to study the local site conditions. And generally the site response depends on the you can say type of the soil, whether the soil is compacted or it is very loose, the thickness of the soil, whether these are a few tens of meter thick or hundreds of meter thick, and stiffness also. And as I already told you in the previous slide, some soil deposits amplify the bedrock motion, some soil deposits de-amplify the bedrock motion, and some soils do both kind of this phenomena. And this is a very classical example. There was an earthquake of magnitude 8 in the city of Mexico, not in the city of Mexico, that was experienced in the city of Mexico, and the epicenter was almost 350 kilometers away from the Mexico city. The magnitude was 8.1. And the Mexico city is comprises of, you can say, some of the areas are located on, you can say, stiff soil or soft rock, and some of those, you can say, areas are located on soft clay also. So they have two stations, one in the you can say installed in the rock and one in the soft clay, and you can see the response of this instrument of the same earthquake at the same distance. The maximum peak acceleration recorded the station located on the rock is around 0.03 G gals, and the maximum that recorded in of the station acceleration recorded at a station which is recorded on the soft sediments is 0.15 G. You can see though the epicenter is same, the magnitude of the earthquake is same, the epicentral distance is also the same. The you can say the wave get amplified almost 5 times. So this is a classic example of local site effect. So that is why it is very important to study the local site effect. And this is a very brief introduction, but we have I have given you about the earthquakes, the different branches of the, you can say, seismology, you can say observational seismology, physical seismology, applied seismology, and then engineering seismology. Why this is important and why it is important to study the seismic hazard phenomena. And these days a lot of you can say efforts have been made by government of India to, you can say, assess the seismic hazard of different cities, because these days a lot of concept has been, you can say, a smart city concept is very coming up. So the government wants to do seismic microzonation of all the smart cities. So by doing the seismic microzonation or assessment of seismic hazard of those cities, generally they will get the information about the, you can say, up to the level of ground motion which can be expected in that particular city. So by knowing that, by the knowledge of that information, they can design the future, you can say they can design the future structures or infrastructure based on those ground motions, and they can strengthen the existing lifeline structure like hospitals and schools also by assessing those you can say waveforms. Now I'll give you a brief introduction about there was an devastating earthquakes in the state of Gujarat that happened in the, you can say, Kutch district near Bhuj in 2001. Of that, the magnitude of that earthquake was almost 7.6 on the movement magnitude scale, and due to this, a lot of destruction has been, you can say, noticed in the Kutch districts particularly, and a lot of destruction has also been occurred in this, you can say, Ahmedabad region, Surat region, which is almost more than 200 kilometers from the epicenter. So I just give you a brief glimpse about the local site effect. So the destruction in Ahmedabad, Surat was partly due to the local site effect and partly due to the, you can say, poor construction practices. So generally, that is why it is very important to make structures which are, you can say, earthquake resistant, and proper study of earthquake site response or local site response is also necessary, so that the structural engineers can take that, you can say, values while designing their structures. So after 2001 Bhuj earthquakes, the Gujarat government has taken an initiative, and they have, at that time there was no institute in India which was fully dedicated for seismological research. Though some seismological studies is being done in IIT Roorkee, in IMD, in Ministry of Earth Sciences, and in some IITs, other IITs, Kharagpur. But as a, you can say, holistically, seismological research was not there in an Indian region. So in 2001, the government of Gujarat has taken the initiative, and in 2004, they have dedicated this, you can say, ISR to the, you can say, state people. And the major vision of Institute of Seismological Research is to save lives and minimize the damage due to the earthquakes. And generally, the mandate is three kind of mandate is there. Generally, we have to monitor the earthquake activity. We are monitoring the earthquake activity in the state of Gujarat by deploying a number of seismic instruments or seismological observatories, mostly of the broadband type in the state of Gujarat, that are spread all over the Gujarat region. Then we assess the seismic hazard, and we try to do research to understand the physics of earthquakes. Our strategic thrust areas are to carry out research on to understand the physics of earthquake process. We also do earthquake precursory research, paleoseismological research. We assess the seismic hazard through site-specific studies or seismic microzonation. We also do a lot of geophysical surveys. And generally, we do both kind of research, applied, basic and applied research. So we have are generally have 6 groups, divided our activities under 6 groups: near real-time seismology, seismic hazard assessment, solid earth geophysics, we earthquake precursory research, active tectonics, and we also do some you can say site-specific kind of studies for different you can say PSUs and different industry people also. That comes under commercial research, consultancy research, and we do a lot of, you can say, study regarding paleoclimate, geotechnical, long-term seismic hazard assessment, earth study, earth structure, hydrocarbon prospects. So these are the diversified fields which we do research in these fields. Then we have a very strong network. We have the, you can say, densest network in India. We are monitoring the earthquake activity. We are installed almost 125 stations comprising of broadband seismographs in the state of Gujarat only. We are having a 24 network station network of GPS, permanent GPS. Then we have a 3 multi-parametric geophysical observatories where we study physical parameters round the clock, 12 physical parameters round the clock for earthquake precursory research. Then we have also doing some kind of array studies for the crustal, you can say, because the crust in the Kutch district is very heterogeneous. So we want to study the composition of that crust. So we have installed an array of 50 broadband stations in you can every 5 kilometers in the Kutch region. So we want to have some 3D structure, crustal structure of the, you can say, of crust in Kutch district. So this study is being done, you can say, first time in India. Then we have a 24/7 seismic data center where we monitor the seismic activity from these 125 seismic stations. And whenever there is an earthquake, we generally report to all the higher authorities. Then we have a geotechnical lab, we have a optical stimulated luminescence lab, geochemistry lab, XRF and sedimentology lab. And we also have a different kind of geophysical instrument to carry out geophysical investigations. Generally, we, as I already told you, we do seismic monitoring for estimation of earthquake parameters. Then we provide the seismic safety factors to different kind of structures. We do basic research on earthquake, you can say earthquake genesis. And then we research and exploration. We do research and exploration of natural resources like water, mineral, hydrocarbon. And this is a kind of network of stations. You can say these are all the stations are uniformly spread all over the Gujarat region, and most dense part is in, because the Kutch region generally comes in zone 5. In the previous slide, I give you a brief glimpse about the seismic zoning map of India. And Gujarat is the only state in India where all the seismic zones are there. Means zone 2 is there, zone 3 is there, zone 4 is there, zone 5 is there. And the entire Kutch region comes under zone 5, where magnitude earthquake up to magnitude 6, you can say up to magnitude 8 can happen. because there are large fault lines are there. They can generate earthquakes up to magnitude 8. Then the Saurashtra region, the entire Saurashtra region comes under zone 3, where earthquakes up to magnitude 6 are expected. Then there is Aravali region that comes under zone 2, and this Narmada region comes under zone 3. And this the Dwarka area, then Mehsana area, that comes under zone 4. So this is the right side, the figure on the right side gives us I told you just an array 50 station array network. So these are the array is deployed in 3 straight lines, and the you can say station distance is around 5 kilometers. Then this is the seismic microzone, you can say monitoring. So these are the stations, and earlier when the observations were a type of analog observation, generally the response time was almost 2 hours. We are taking almost 2 hours to estimate the earthquake parameters. Parameters means in terms of magnitude, location, and distance. Now with this latest broadband seismographs and the connectivity of this broadband to different, you can say our central station, we have brought down this timeline to almost 5 to 10 minutes. There are we have also doing auto location also. Auto location means whenever there earthquake happens, generally it is being automatically located, and we get parameters in, you can say, in few seconds only. But there are a lot of other things are also there. Generally we don't transmit this information to the in the public domain, because a seismologist has to check these parameters, then only we can give it in public domain. So generally we take almost 5 to 10 minutes, and within you can say 5 to 10 minutes we give all the earthquake parameters, this in terms of origin time, in terms of latitude, longitude, and magnitude, and depth also, to different agencies. And we also do just we have a network of almost 25 permanent GPS stations installed all over the most of the stations are in Kutch region, and some of the stations in Saurashtra and mainland also. And but we have seen that the deformation in this region is very low, means almost of the order of 1 to 3 millimeter per year. Where is the because these are this Gujarat region is in plate interior, so that's why the deformation rate of deformation is very low. Whereas if your station or if your GPS station is installed in the Himalayan region, that is an active plate boundary, there the deformation is around 15 to 20 millimeters per year. And here it is around 1 to 3 millimeter per year, the deformation. And most of the deformation, the highest deformation is noticed in the Kutch region. It is maximum is noticed is 3 millimeter per year. It varies between 1 to 3, and in rest of the Saurashtra, mainland, and Narmada, it varies from 0.6 to, you can say, 1 millimeter per year. Then we have an earthquake precursory research. We also do. We have multi-parametric geophysical observatory that is in the Kutch region, where we monitor all the physical parameters. Means we have installed a broadband, strong motion, alpha radon. We monitor the radon emission also. Then we have magnetic instrument. We have a superconducting gravimeter. We have permanent GPS station. We have a digital flux gate magnetometer, overhauser magnetometer. Then we monitor the groundwater level also in this. And we are also doing, ISR is also doing a lot of microzonation and site-specific studies also. So we do these studies in cities, in monument, in critical structures, in commercial building, and special economic zones. So we have done this in city. We have completed microzonation in Bhuj, Gandhidham, Anjar, Gandhinagar, Ahmedabad, and we are doing this in 8 cities in northern India also: Amritsar, Banaras, Dhanbad, Patna. And we have also done the seismic hazard assessment of Statue of Unity, then Dwarka Jagat Mandir, then we are doing for Vadnagar also. And critical structures, we have done seismic, you can say site-specific studies or assess the seismic hazard of nuclear power plants, LNG and LPG terminals, hospitals, different dams, solar and windmill sites, then boilers and naphtha cracker plants. And we have also done this seismic hazard assessment for Gift City, Dholera Special Investment Region, Dahej region. So these are the activities that we are doing. So these are cartoons showing the different site-specific seismic studies which we have done in last, you can say, 10 years. And then we have, based on all the information which we have collected in last 10 years in terms of seismological information, number of earthquakes along different faults, then we have collected information about local site conditions by doing a lot of geophysical surveys all around the Gujarat region. So we have come up with a, you can say, surface level acceleration map of different districts. We have prepared a surface acceleration map of different districts. Means if you want to design a normal kind of building, means 1 story or 2 story, you can directly take this information and design your structure according to this, you can say different seismic factors. So these are the advantages of doing different kind of studies in a single institute. Means we have a lot of information about the geological site conditions all around the Gujarat state. We have information about active faults in the Gujarat region. So we have utilized this information and produced this kind of maps. Then we also do science for the society. Means we do a lot of geophysical surveys for petroleum industries, for you can say hazard with generation of hazard maps. Then we also do geophysical studies for harnessing the geothermal energy. Then we also do geophysical surveys for groundwater exploration also. And we have done this, we have delineated some freshwater zones in Kutch region, which this is a very strategic, you can say, these zones are located at the depth of 200 to 300 meters. So generally we don't tap this kind of resources. Whenever there is an emergency only, then only these kind of resources are, you can say, trapped, because it is very difficult to, you can say, replenish these zones. So we have identified some zones in the Kutch region where the fresh water is available at the depth of 200 to 300 and up to 550 meters also. Then we have done geophysical surveys. We have done passive seismic surveys for the oil industry, for ONGC also, and GSF, this Gujarat company also. We have done this for this also. So this is, we have utilized the local noise, because a lot of, whenever you install a seismic sensor anywhere in the ground, there are a lot of background noise is already there. So we have utilized that noise information, and then we have given some prospective location where oil can be, you can say, there is a possibility of, these are called sweet spots. So there is a possibility of getting oil in those regions. So we have done some pilot studies for ONGC also. And we do a lot of outreach activities also. We distribute the earthquake information. Then we have made some documentaries. Then we participate in Gujarat School Safety Weeks. And then we communicate all our, you can say, research which is useful for the society in the print and media. And we train geosciences, geotechnical instruments, you can geotechnical students from different engineering colleges and different parts of India also. We also do tsunami studies. We have done some simulation exercises for if the last earthquake, major earthquake that has happened, or the earthquake that has generated tsunami in this Arabian Sea, that was in 1945. From that earthquake happened in the, you can say, Iran region, the Makran fault. There was an earthquake of magnitude 8.5, and the tsunami was generated due to that earthquake, and a lot of areas in the Gujarat coast got damaged due to the tsunami. So we have simulated that tsunami, and we found that the maximum amplitude was almost 2 meters that was noticed, that was in the Okha region, Dwarka. It matches with the amplitude that was approximately noticed in that region. We have prepared a deterministic hazard map of Gujarat based on all the information that we have collected. We have prepared a basement map also. We have prepared a Moho depth also, Moho depth map also. So we have prepared the characteristic site frequency map also. This is useful for the engineering design of different kind of structures. We have produced a site condition map also. So we have given different geoelectrical models also. And this is a very interesting study which we have. There was a, I think last year in 2020, there was a flood in Uttarakhand near Rishi Ganga. A lot of damage were noticed due to that. So we have, because there are some seismic stations which are being operated by Indian Institute of Remote Sensing, Dehradun, in that region. So we have studied those because this is due to a, you can say, rockfall triggered disaster. So when that rock fell almost, you can say, 1800 meters from top of that mountain to the ground, a lot of, you can say, energy has been generated, and due to that is recorded, that fall has been recorded in different seismometers, that stations that were you can say installed around that region. So we have studied those rockfall, those waveforms, and doing a simple kind of modeling. We you can say propose the theory that it started at the time of started and how the debris flows in that area and why the destruction, so much of destruction was there. So this was a different kind of study. And you know that during lockdown there was all the activities were stopped by government, all the industrial activities, all the vehicle movement was stopped by government. So that was a very, you can say, good time to study, you can say, the studies on different ambient seismic noises, because most of our seismic stations are located either near the highways or near some large cities, and we are recording a lot of noise also due to the anthropogenic activities. So these kind of activities generally were not there during the corona lockdowns. So the signal to noise ratio was enhanced during that period. We were able to, you can say, record earthquakes of magnitude 0.2 and 0.3. Very low magnitude earthquakes we were able to record. So we have done some kind of research of effect of coronavirus lockdown on the ambient seismic noise, and that was published in Nature Scientific Report. So thank you very much. This is all I want to, you can say, discuss about the seismological research, and you can say different initiative, a good initiative taken by Gujarat government after this 2001 Bhuj earthquake. So this is a very fundamental type of, you can say, lecture, not very detailed.
Thank you. Thank you, Dr. Chopra, for this nicely informative and then
Thank you very much.
talking about various characterizations and various zones in Indian sector and other aspects. And also you talked about the mandate of ISR and the service that you are providing to the nation. Thank you very much. And now I'll request my colleague, Sanjeev, to do the question answer.
So, thank you, Professor Raju. Thank you, Dr. Chopra. It was really nice talk. I think it is very nice for people who has no background in seismology to understand the earthquakes, its regions, and reason for its occurrences. And definitely your detailed work in Gujarat and wider mandate of ISR. So now it's time for question and answer session. And there are two platforms from which people have joined, that is Webex and YouTube. So I would like to invite people from Webex to ask you questions. So colleague, whoever have questions, they can raise their hand and I will call them. So maybe they are warming up to it. So I would request, okay, Dr. Som Sarma has a question. So Sarmaji, please go ahead. Hello.
Yes. Am I audible?
Yes, yes, you are. No, I'm requesting Dr. Som Sarma.
Yeah.
Thank
you, Sanjeev. Thank you, Dr. Chopra, for very nice and you can say pertinent, which is very, very important for all of us like that. So just I have one query, as you have addressed in last like that, there are anthropogenic, you can say, disturbances which affect like that to detect small earthquakes. So in India, there is a very large network of, the trains, and the train frequencies are increasing day by day from east to west, north to south. So how these train movement is affecting the seismic network in different region of the India, and is there any way to you can say mitigate that disturbances due to the train movements, the Indian Railways movements, which are increasing day by day?
Yeah, that is a good question, because a lot of infrastructure, you can say, in terms of road network and train network is being, you can say, increasing in day by day in India. Actually, there are two options. Generally, whenever we locate an, you can say, ideal site for the installation of seismic instrument, we go away from the, you can say, city or a village. But sometimes it is not possible to go, you can say there are some logistic issues are also there. So nowadays we are preferring a, you can say, a borehole sensors. Now borehole sensors are also becoming popular. These are very costly nowadays because a surface sensor you can get it around 5 to 10 lakhs, but borehole sensors is almost 25 lakh rupees a single sensor. But I think in the coming years the cost will definitely will come down when more and more people will use that borehole sensors. Then the cost will come down and these noise can be reduced, because these noises generally mostly in the top, you can say 20 to 30 meters. This noise will affect up to 20 to 30 meters. So if you install a borehole sensor maybe around 30, more than 30 meters or 50 meters, then you can avoid this kind of you can say noises due to train or some road traffic.
Thank you, Professor Chopra.
Thank you, Samaji. Dr. Chopra, can you remove your slides here, please, so that we can see you in bigger screen?
So I can
Yeah,
stop sharing.
Stop sharing, yes.
Okay.
Thank you. So now I see a hand raised by our director, Dr. Anil Bharadwaj. Sir, please go ahead.
Thank you, Sanjeev, and thank you, Dr. Chopra, for a very excellent talk, summarizing the seismological research basics and then going into details of what's happening all over India and the world, and then particularly talking about Gujarat. And that's also very important for all of us because Gujarat is a state where we are staying. I had just two questions. One is more basic. In terms of understanding that now we know that earthquake is being caused by plate tectonic and movements, essentially plate movements. So why it is becoming still very difficult to make prediction of when it is going to happen, when we know that the movement of the plates, even the rates we are now knowing. So what is causing? Is it that we still do not understand the interior part of the earth to that extent, and because of which the processes which is happening inside, maybe 10 kilometers down, which we have not explored into great detail, is the uncertainty which is causing that we can't make a prediction about the earthquake. We can say it will happen sometime, but when it will happen, or at least within 1 month or within a few days, kind of thing.
Yeah, you are partially right in you can say the giving the explanation. Actually, what happens because most of the earthquake activity is happening around at 20 to 25 kilometer depth, and we have still not understood the you can say the physics, actual physics of earthquakes, because we can drill hole only up to 8 to 10 kilometers. So what is happening at the 20 to 25 kilometers depth? It is very difficult to you can say what is happening at that. The day we can drill up to 30 kilometers, 25 to 30 kilometers, and deploy all the instruments at those depths, then we can able to understand what is going on there. And I think recently the Ministry of Earth Sciences has taken an initiative, and they're in the Koyna region, they are doing a deep drilling project. So they have you can say come up with a borehole geophysics laboratory. So there the earthquake activities you can say reservoir based, reservoir triggered activity, and there the epicenter is very shallow. You can say the focus is the focal depth is around 5 to 6 kilometers. Most of the earthquake activity is around the 5 to 6 kilometers. So they are drilling a hole up to 8 kilometers, and they will deploy all kind of instruments at those depths, and they will then monitor all the physical parameters what are happening at those depths before an earthquake, during an earthquake, and after an earthquake. Then in future we can able to propose some kind of model for earthquake prediction.
Thank you for this explanation. So I was also thinking in the same line that probably we still don't understand the interior part of earth very well, and that is what is causing. And the second uncertainty probably is that the energy of the stress and strain which you're talking about, which gets built up.
Yeah.
Do we have a good assessment of that how much is the actual built up, or we say that it is building up, but the magnitudes are not very clearly known?
Actually, this is I can explain you with one illustration, because we have, suppose we have a steel glass. So we start filling the, you can say, water on this steel glass. We know the amount of water which we are adding, but we don't know the amount of water which is already there in that glass. So some of the energy is already stored in that glass. We are not aware of that, but whatever energy is, you can say we are adding due to this plate motion, we are well aware of that. That is why it is very difficult to say the total energy which has been stored in that. And during an earthquake occurrence, this energy generally get released, most of the energy, but there is one creeping effect also. You can say slow earthquakes also. During slow earthquake, there was no acceleration will be recorded on a sensor, but the energy will you can say released due to the creeping effect, that we are not aware of how much energy is released due to that creeping or this slow earthquakes. So that is the difficulty.
See. Okay, thanks for the good explanation. My last question to you. With our improvement in understanding the earthquakes and our plate tectonic movements, and within India, is there any change in the zone demarcation in the recent years compared to what it has been done once?
Actually, the zone is mostly what we are seeing, the seismic zoning map of zoning for dividing into, you can say, 4 parts. This is almost means it's okay. Now the main question is that India doesn't have any because most of the advanced countries, European countries or Northern American continent, they have a probabilistic seismic hazard map of that country. So most of the engineers generally demand that PSHA. So India is lacking in that part, because we do a lot of research. We have developed some PSHA map of Gujarat. Somebody has developed PSHA map of Northeast India, but there is the Bureau of Indian Standard has not done that. But recently, that task has already been completed, and I think within 2 to 3 months you will get a BIS code on PSHA. You will get a PSHA map. There you will get a different kind of zones, more zones than this you can say zonation map.
Okay, great. Thank you. Thank you very much.
Thank you, sir. Thank you, Dr. Chopra, for answering. Next question has to be from Professor Abhijit Chakrabarti. Please go ahead, Professor Chakrabarti.
Very nice talk. Thank you very much. I have just one quick question, is that you talked about the earthquake due to reservoir induced earthquakes. So I wanted to know is that, we have this Narmada Dam, which is very large, right? And it is sitting on the river Narmada, which is also sort of I don't know, you're the expert on that. So, so what is the, are there any work on any research going on that what is the probability that there can be some, earthquake because of, if not large, but maybe up to 6 magnitude or so, due to the reservoir. Is there any work done on that, or probability? What is the probability?
Yeah, actually, I started my career in the Sardar Sarovar Dam only. So at that time, we have installed a network of 9 seismic stations around the, you can say, dam, around the reservoir. So the 3 stations were in Madhya Pradesh, 1 in Maharashtra, and 5 were in Gujarat. So that process has been continuously being done since 1988. Now, after the formation of ISR, we are monitoring that activity with latest digital equipments. So we have a data of almost 30 years, and now I can you can say with some level of confidence that after the construction of the dam and with the filling of the reservoir, the seismicity has gone down in that region. So we are recording a less number of earthquakes. So this is a major outcome of having a network of seismic station and recording very small earthquakes for the past 30 to 35 years.
What could be the reason for that?
Actually, generally now the terminology is not induced. We generally call it a reservoir triggered earthquakes. Means there is a lot of strain energy is already being stored in that region. These reservoirs, the effect of this loading, only the trigger of, they can only add a small amount of stress. So if the region is already strained, if you apply a small stress in that region, then the small earthquakes generally happen. And generally these kind of, you must have a, you can say, normal. There are 3 kinds of earthquakes: normal earthquakes, reverse type of earthquakes, thrust earthquakes, or strike slip earthquakes. Generally, if the region is recording earthquakes which are of, you can say, normal types earthquakes are like that, where the rock generally slide past each other and the one block goes down and one block goes up. So with the loading effect, if your tectonic environment is like a normal kind of environment, then only reservoir triggered earthquakes, generally phenomena happens. And fortunately, in Narmada region, the area has a thrust kind of environment. In thrust kind of environment, one rock you have to block goes up and another goes down. In that region, more energy is required to, you can say, generate that earthquakes. So the tectonic environment is not conducive for reservoir triggered kind of activity in the Narmada region. Whereas in the Koyna region, the tectonic environment has a normal kind of activity, means normal earthquakes are being recorded in that region. So that is the main reason.
Thank you, Will.
Thank you, Dr. Chopra. So next person who's going to ask you a question is probably most interested in your work. He's from Bhuj. Dr. Haris Gadri, go ahead. Haris, you are muted. Maybe you are muted. Just check it.
Hello, sir. It was a very wonderful talk. Probably you know my brother, he worked with you, Mahendra Singh Gadvi, on the earthquake. Actually, my question is based on one science fiction novel I was I read some year back, and in which geoscientist is a villain, and he knows everything about the faults and strains and everything. So he knows the point where he wants to do a blast, and he does the blast, and then he sends a big earthquake into the city. So my question is that how far we are from worrying about the artificial earthquake our enemy is sending, or somebody like rogue actor sending it.
No, actually, it is very difficult. You see the Himalayan region, a lot of strain energy is already stored there. So a lot of earthquake scientists or earthquake engineers or different geoscientists have predicted that a large earthquake or a great earthquake is due in Himalaya at any time. So, but it is very difficult to say when it may happen. But as you are saying about this blast or local blast, this is a very fraction, you can say, fraction of energy which you can say impart to the rocks. So this is almost negligible, and due to this, the magnitude, maximum earthquake magnitude may be around 2 to 3. That may happen. You cannot expect an earthquake of magnitude 7 or 8 due to this kind of activity.
So it's not possible like use some points as a trigger and just give little boost.
It's very difficult.
But there was some news in I think in scientists in Switzerland or somewhere. There was some earthquake triggered because of fracking, and then the geoscientists were put into the jail because they given the permission for fracking. So, of course, there were minor earthquakes. But how does the fracking actually causes the earthquake?
Pardon, I couldn't understand your question.
Fracking, for the oil wells, they kind of put some.
Oil injection.
Yes.
Actually, due to this, this is actually regularly being noticed in the, you can say, in the American region. So they have done a lot of, you can research in this fluid earthquake due to fluid injection. But the magnitude of those earthquakes is very small. You can say hardly it goes up to 1 to 1.5 or maximum 2. The magnitude will be very small.
Okay.
You may experience, you may not experience also.
Okay. Thank you, sir. Thank you very much.
Thank you, Dr. Chopra. Next question is from Durga Prasad. Dr. Durga Prasad, please go ahead. Ask a question.
Thank you, Dr. Sanjeev. Thank you, Dr. Chopra, for a very informative talk. I have two questions. In one of your slides, you have mentioned that most of this strain energy is converted into heat rather than the vibrations. So is there any quantitative evaluation of that?
Quantity, actually, the earth, the inside the earth is so complex. It is very difficult to quantify that figure because it varies from, you can say, region to region, and it varies from different. It is different for different tectonic environments also. So sometimes it is 3 to 4%, sometimes it is 10%, sometimes it is 3%. It depends on the tectonic environment. So it is very difficult to quantify a single value of this. So a lot of research has already been done in different parts of the world, but that is applicable to that region only, to that fault only. So it is very difficult to, you can say, generalize that you can say figure, whether it is 3.5%, 4% or 5%.
So I have a follow-up question with this. Like if you can, if we can precisely monitor the temperature variations at different regions, and correlate with the seismic data. So will it be possible, like as you said, 30, 35, 40 years data set, will it be possible and help in future predictions?
Yeah, it is possible that I was telling about that this Koina project. So if you have to put that temperature sensor inside a borehole up to the, you can say, focal depth, means up to the foci, means 7 to 8 kilometers at different levels, then it is possible to get this kind of, you can say, you have to model that region, and then you can say how much energy is going converting into heat and how much into seismic waves. Then it is possible.
I have one more question. Actually, just after Bhuj earthquake, so a lot of constructions, multi-story constructions were stopped. Permissions were denied. That I could see from 2009 after 15 years. But recently, we see several multi-story constructions were permitted in Ahmedabad. How do we take up this? So is that it is not seismically active or a hazard is not there? Are they are well planned?
Actually, you can construct any kind of building in any environment. Whether if you are in zone 5, you can construct single story also, 100 story also. And if you are in zone 3, just like Ahmedabad, you can construct any type of building. But you have to take a proper, you can say, you have to assess the seismic hazard. Generally, whenever there is a tall structure is being made anywhere, you say in any city or anywhere in any region, means more than 20 story, 30 story, 40 story, they generally do site specific studies. Site specific study means they do geotechnical investigation, geophysical investigation, and they give this. We are doing a lot of this kind of activity. Then they properly assess the seismic hazard due to a local earthquakes and due to a distant earthquakes. Then they give a response spectra that will give you the information about the amount of forces for which you have to design your structure, because the amount of forces will be different for a different height of structure. Means for a single story structure, the amount of forces, earthquake forces, will be different. For a multi-story, it is a little different, though the site is same. So that is the beauty of doing a site specific studies. The destruction in Ahmedabad, I will tell you about destruction. If there is a large earthquakes in the Kutch region, the high-rise building will be more affected by that earthquakes. And if there is a local earthquake within a 50 to 100 kilometers near Ahmedabad, then the low-rise building will be affected, high-rise building will be safe. So that depends on the distance of the earthquakes from your affected region. Because the distant earthquakes, if you are recording in Ahmedabad, Kutch earthquake, if you are recording in Ahmedabad, the seismic energy which we are getting, that is rich in low frequencies. And most of the, you can say, high-rise building has a natural low frequency, low frequency. And if you are recording a local earthquakes within, you can say 50 to 100 kilometers, then the seismic energy is rich in high frequency. And most of the low-rise buildings has a, you can say, high frequency, natural frequency. So you have to look into the distance of the earthquake also. So that is the response spectra which we give to the engineers. It encompasses all the frequencies. It takes care of distant earthquakes also, regional earthquakes also, and local earthquakes also.
Okay. Thank you very much.
Thank you.
Thank you, Dr. Chopra, for nicely answering that question. The last one particularly is interests all of us actually. The last hand raised I see on the WebEx is Dr. D. Banerjee. Dr. Demarcation Banerjee, please go ahead and ask your question.
Dr. Chopra, thank you for a wonderful talk on seismicity in India and in Gujarat. My questions, I have a couple of questions. One has been asked by our director, but I would like to ask you further on that. I mean, would it be fair to say that the repeat frequency of major earthquakes in the Himalaya is of the order of a decade, and in Gujarat, it is of the order of 100 years, based on data? The second question is, why isn't there a very strong program which looks at the paleoseismic record, of earthquakes in the Himalaya or in Gujarat? I think the paleoseismic record and then the slip rates will give you some indication of possibly the repeat frequency of the major earthquakes, which we should worry about. So can you throw some light on these two questions? Thank you.
Yeah. Yeah, actually the recurrence interval of you can say earthquake of magnitude around 6 to 6.5 is around you can say 30 to 50 years in Himalaya region, and in you can say in this part of you can say stable continental region or peninsular India, it is order of more than 500 years. So the recurrence interval is generally very large in the stable continental region in comparison to the plate boundary region. And regarding the paleoseismic studies, a lot of paleoseismic studies has been carried out in the Kutch region, and the Ministry of Earth Sciences has already taken initiative, and they have already given us a project to different agencies. ISR is one of the agencies, so they have done paleoseismological investigation across different faults in the Kutch region, and they have now they are coming up with a you can say active fault map of the Kutch region shortly, within I think within 4 to 5 months. So that will answer most of your questions.
Thank you.
Thank you.
Thank you, Dr. Chopra and Dr. Debrata Banerjee. Now I'll go to the YouTube channel where there are two questions from Professor Ashok Singhvi. First of all, I must say that he has paid you high compliments for your talk, well delivered. So the first question from him is, what is the physics / material science of clays amplifying the seismic waves and hard rocks do not?
Actually, generally the loose sediments, because we have to conserve a lot of you can say energy. So the loose sediments, you can say the shear wave velocity in these loose sediments is very you can say very small, means of the order of around 200 to 300 meters per second, whereas the shear wave velocity you can say hard rock is around you can say more than 500 or sometimes around 700, 800, and sometimes very hard rock more than 1500 meters per second also. So when the sediments are very you can say loose, you have to conserve that energy, and that you can say that's why the amplitude gets increased. And generally it depends on the you can say the frequency content also. So if you are incoming or frequency content of the incoming seismic waves is rich in low frequency, then these get amplified. But if it is rich in you can say high frequencies, these get generally de-amplified in these soft sediments. Whereas in the hard rock region, these high frequencies get generally amplified, and in this hard rock region, because the attenuation is very low in this region and attenuation is very high in the you can say soft sediments. That is why wave gets amplified in that region in you can say in comparison to the hard rock.
Thank you, sir. So through next question, probably he wants to probe your role as a director ISR. So the question is, what plans does ISR have to develop instrumentation in-house?
This is very difficult. At present, you can say any plans, but we love to do that thing. We develop at least simple kind of sensors, but presently we don't have any plan. That is a good suggestion. We have to, I think, we have to take this suggestion positively.
Okay, thank you. So, and this is probably the last. This is the last question, not probably. This is the last question, and maybe you have answered in a way to your answer to our director. The question is, how close we are today to predict the earthquake?
I think we are far away. Still, it is very difficult to predict earthquakes. We have to the drilling exercise is going on. This has been done in different parts of the world already. This drilling, they have put a lot of instrument in across this San Andreas fault. They have put, but still they were not able to predict that earthquakes. They have predicted an earthquake of magnitude around 6 in the San Andreas fault near California, in I think in 1991. The earthquake then happened there in almost after 15 years, in 2005 and 2006. So still we are far away from predicting the earthquakes.
Okay.
So it takes a lot of time.
Thank you, Dr. Chopra, for presently answering all the questions we had. And now we have reached to end of the question and answer session. Now I invite my colleague Dr. Durga Prasad to give vote of thanks. Dr. Durga Prasad, please go ahead.
Thank you, Dr. Sanjeev. So on behalf of the director PRL Amrut Vyakhyaan committee and the entire PRL family, I thank our today's Vyakhyaan, Dr. Sumit Chopra, for accepting our invitation and delivering the 56th episode of our 75 Vyakhyaan series. He has provided us an insight into the ongoing seismological monitoring and hazard mitigation and aspects of current seismological research, and mainly the new initiatives taken by Gujarat government post-Bhuj earthquake. Thank you very much, sir, for your very informative and amazing Vyakhyaan, and also patiently answering all the questions of our viewers on both YouTube as well as WebEx. I thank our director, Professor Anil Bhardwaj, for his constant support and encouragement so that this Vyakhyaan series is going on. I thank our Dean, Professor Pallam Raju, Professor Nandita, Chair, and Professor Lokesh, Co-Chair, and all other members of Amrut Vyakhyaan Committee and others behind for their constant efforts. Most importantly, lot of thanks goes to our participants and viewers who have joined us live today through WebEx and YouTube for this Vyakhyaan. With this, we come to the end of this episode. Now we sign off from PRL, but stay tuned, keep following us, and see you all next week with another interesting and new Vyakhyaan. Thank you very much.
Thank you. Thank you, sir. Thank you very much.
Thank you. Thank you so much, Sumerji. It was a really wonderful talk, and we all enjoyed and got enriched by the knowledge which you have as well as the work which your institute is doing.
Yeah.
Thank you.
Thank you, sir.
Thank
Bye.
you.